My name is Addison Huddy. I work for Pivotal, and I work on something called Apache Geode that we're going to talk a little bit about today. If you don't know, Pivotal Software, we work with companies. We build tools, we have methodologies, and a platform to help big companies make better software and try to deliver more business value to their customers. I can tell you way more about that, but we need to answer this question. So who's used an in-memory data grid before in the room? Sort of? Okay, I'm glad I didn't see any hands because you're in the right place. If you could answer this question, you probably shouldn't come to this talk, but I'm glad you guys are here. So, how we're going to answer this question, I'm going to tell you a little bit about how I stumbled upon in-memory data grids totally by accident and why I like working on them. Really briefly, show you some real-world use cases of customers I've worked with in the past. But more importantly, and where we're going to spend the most amount of our time, is we're actually going to work together to build an in-memory data grid. Does that sound like, are you guys up for that? You guys want to, yeah? Okay, like I'm going to need your help. So, all right, and then we're going to design an in-memory data grid, and then we're going to think about some use cases. So it's a little bit, technology for use case sake, but let's just spend that for a little bit. In-memory data grids provide a lightweight, distributed, scaled-out in-memory object store, the grid, and multiple applications can concurrently perform transactional and analytical operations, and low latency, thus minimize the access for disk-based systems. Job done, definitions there, Gartner solved it for us. So, first time I read this, this was kind of my thought. I just thought of like a grid and computers. But then someone explained it to me, they drew some pictures, and the first thing that came to my mind was, has anyone seen the movie Swordfish? Okay, no? Well, there's a scene in it when Hugh Jackman does some really awesome hacking, and he creates this thing, and it looks like that, and that's what came into my mind was this grid. And we're gonna draw a lot of boxes. Look how happy he is, see? So, all right, so two examples of where this is used. It's in extremely low latency use cases with a lot of throughput. So I find it very interesting to look outside the US because I think that is where a lot of the most data intensive use cases are. So for example, one of the customers I work with is China Railway. 1.4 billion page views per day, 20 million daily users, and there are 40,000 visits per second on their site. So really high scale, and they need to deliver answers that are right every single time. And I mean, they're doing a ticketing system. So if I buy a ticket and that's the last one, you can't buy that ticket, and they got to make sure that that's right. Another one is Southwest Airlines. I work with them very closely. First, just want to say my condolences to those that were injured or lost on 1380 yesterday. And I'm pretty amazed with the professionalism that they handle that situation. But if you think about what they have to do is they're tracking over 4,000 daily flights, the passengers that are on that flight, where they are, all of that, and they need to do it correctly. So, when not to use in-memory data grids, really quickly, when you have small amounts of data, latency isn't mission critical, and you need to do some analytics using SQL. They will not replace a traditional relational data store. All right, so let's make an in-memory data grid. And this is where I'm going to need your help. So the design goals of making this system is going to be extremely low latency. We need high throughput. The system needs to be durable. So if, let's just say someone trips on a network cord and we need the data to still be there and to be able to recover. We need to support large data sets. So the amount of information that needs to sit in memory and be accessible is very high. And then we're going to talk about consistency a little bit. And I'm going to argue that our system should be consistent, meaning every read gets the most up-to-date write. So, how we're going to solve that? we're going to go through each one of these, and this is my proposed solution to get these answers. If someone has a different solution, shout out and say, no, that's a terrible idea. So first, I will say I work on Apache Geode. I work on a distribution of Apache Geode called Gemfire that Pivotal puts out. So a lot of my design decisions are going to be based off the fact that I know this system really well, and the end solution is probably going to look a lot like Apache Geode. But just want to say that. All right, so memory first. Memory first. I think we should use memory as our first storage mechanism in the system. Anyone disagree? All right, memory first it is. So why we want to do this? Has anyone seen these latency numbers before? Yes? All right, so this was put out by Jeff Dean, and it's attributed to Peter Norvig as well. And it's latency numbers every engineer should know. Talking about how long it takes to get stuff out of an L1 cache all the way down to sending a packet from California to the Netherlands and back. When I first saw these numbers, and these are on GitHub and people update it and stuff as hardware gets better, but when I first saw these numbers, they didn't really, I don't think on nanosecond scale like Jeff Dean. Like I'm pretty sure Jeff Dean he can count in nanoseconds, but I can't, so I had to scale them up. And I looked at memory, an SSD, and disk. And if you think about Amazon Prime, an Amazon Prime delivery being how long is the base of how long it takes to read 1 megabyte from memory, and you scale everything else up, that means an SSD read of that time is going to take 9 days, and a disk is going to take 8 months. So that's the differences in time. Now, I don't know about you, but I'm really mad at Amazon when they miss my delivery by like a day, let alone 9 days or even 8 months. So this is kind of why memory and the use of memory is so important. All right, so next thing we want to talk about is horizontal scale. We need to be able to add nodes, take away nodes from our distributed system, and it all needs to be done in memory. And the fact that it's going to be horizontally scalable, we're going to be able to grow our cluster and meet some of those memory requirements in our system. Because I don't have the money to go out and buy the largest amount of memory possible to put on one machine. We need more commodities hardware and distribute it out. So, drawing some boxes and some lines, this is how I think about an in-memory data grid when I draw it. So really quickly, the colors that are up here, I'm proposing that we do a client-server architecture where our clients can talk to our server. Down here, I'm proposing that we have some processes called locators that constantly watch the system and make sure, like, okay, what nodes are talking to what nodes, what's available in the system, who's going out, who's going in. So that's what they do. But really quickly, what we have here is we have 4 pieces of data that are each represented by a different color, and they're distributed throughout the system and copied twice. So the redundancy level within the in-memory data grid is 2. So that means that if a client produces some data, and again, I'm skipping over the fact this is a key value store. It's a key value object store. So I create an object, I have a key, I have a value, and I put that in the system. The next thing it's going to do is it's going to write here, and then I'm going to argue that the client shouldn't get confirmation until it's copied over at least once, because that's what the user specified the redundancy level to be. So a single write into our data grid is going to be once here, it's going to be copied here, or in this case over here, and then the client will say, yep, we're good. All right, so, someone tripped over a network cable in the data center, and we lost it. We lost 2 machines. The locator said, can't see them anymore. 2 members of our grid went down, and that data then, the system will recognize that and copy the data and balance it between the 2 remaining servers that we have. So that horizontal scalability and elasticity will meet some of those requirements that we had. So if we add another node back into the system, a machine comes back up, someone restarted the EC2 machine, whatever, we have that node back in our system, and the data will be balanced throughout. So now we have this horizontal scalability, everything's in memory, and you get super low latency. Job done. So I mentioned really quickly a quick aside of where these systems and our system, which looks a lot like Apache Geode, falls on the cap theorem. Well, it depends. I made the assumption earlier that we wanted things to copy synchronously between those two nodes. Now, if we had chosen to copy them asynchronously, what do we change in our system? Where would we be on the cap theorem? Yeah, we'd be AP. So the system we were coming up with was sitting here on consistency and partition tolerance. But if we had changed what we wanted to do between those two nodes, we're going to sit up here on an AP system. Now, these I put up here, these are all the default settings in these systems and a lot of the in-memory data grids that are out there. They're configurable, but I won't go into that. All right, so now that we have this quick aside, this is a feature that I want to add into this in-memory data grid, WAN replication. So we have this client-server architecture, and I think that we should have asynchronous communication between the two data centers that we have up here. And this is one of the really popular features that a lot of customers use today, where if I have a write, let's just say a data center in New York, a write happens, we get confirmation back to the client, the two clusters will maintain consistency over an asynchronous communication between these two data centers using WAN replication. That's another feature that a lot of customers use, and I propose that we put in our in-memory data grid. All right, the next thing we've done, we've used memory, we've used horizontal scalability to capture some of our design goals. The third thing that I think we need to add is data-aware routing. If we go back to that latency diagram, what's this here that's causing a lot of our latency? It's network. So the network is going to add a lot of latency. So if we have this grid, we've kind of designed this grid here. Every hop on these black lines is going to really cut down our latency. And we have the data distributed amongst all these nodes. And when a client wants to do a read, it might go in and say, okay, the data isn't here. It's actually on a different part of the system. And that's going to have another network hop. So the way to solve this is we need to add some smarts into the clients to say, and give the client some knowledge on what node in our grid has what data. And that's what a lot of these systems do. So customer comes in, they have a certain key, a certain value, they want the purple object here. Our client is going to know that the data is on this server, rather than coming in, looking, saying, I want the purple one, and maybe, again, I kind of skipped over something. Every one of these clients maintains a connection with each one of the servers. So if I round robin through all of those connections, I'm not going to necessarily find the data because it's not replicated on each one of the nodes in our grid. So by adding this single hop feature into our clients and making our clients know where the data is, we can skip that really costly network hop and get that latency down. The next thing that we can do, because our clients have a little bit of smarts in them, is we're going to add a local cache into our clients, and that'll save us yet another network hop. So a client comes in, let's just say they log in, and they have a session in their browser. Now, since I have a copy of that object here in the client, I don't have to go to the cluster, thus saving a costly network hop. But the thing that we just introduced into the system that has a lot of complexity is we have to worry about expiration of that object. So if something changed in the server, something that we added to the system, like a function that's running that says, when a certain threshold gets met, change this object, add something. We then have to add a bunch of communication that's going to happen between the server and the client to say, that locally cached magenta object up there, it's old, and you need to get rid of it. And here's the updated one. So a lot of complexity happens in this grid, but it's going to save us a lot of latency, and that's our big goal. Serialization, I'm not going to go a lot into this. I feel like we could have, it could have its own track at this conference just on serialization. We'll have to talk to Pete about that. I don't know if does anyone want to like be a speaker at serialization track? I don't know, it might happen. We're getting some traction. But this is a really big piece of saving latency and increasing throughput. So without going too much into serialization, there's a lot of serialization formats. The way that in-memory data grids, and I think that we should solve this, is creating our own serialization format. But the 3 rules in my head around serialization, serialize and deserialize only when it's necessary. So for example, if we go back to our system, we want to try to just read. We don't want to add CPU costs here and here when we move data across the wire. That's going to save a lot of costs in our system. So only deserialize and serialize when it's absolutely necessary. Only deserialize and serialize what you need when you need it. So I'm not going to get into this, but a lot of these systems support server-side functions, or you can bring some in Apache Geode's case, a function to the server that runs there, and you can do things like real-time processing or event queues or something like that. And if we have this big object that we're storing, if we need to look things up in it, and we kind of take it out of memory and try to look at it, that's going to be really costly. So we need to be able to look at that object and the only things that we want in that object. And the last one is we need to distribute the deserialization costs as much as possible. So if the server is sitting there doing all that translation, getting the object into one format, another format, getting over the wire, if we have that all sitting in our servers, it's going to be really costly. So the thing that I'm going to propose is that we take that serialization and we distribute it. So that deserialization back into something like an application's domain object is going to be done on the client. So now we have all these clients that we can spin up a lot faster doing our deserialization work for us. So basic user so now we have the system. It's a super low latency, high throughput system that we probably can have some basic user operations on. And the features that I think we can create here, put and get, we've seen that. We've seen that I can take an object, I can put it, I can get it from the grid. I can do queries against the grid because we have all this data sitting in memory and I probably want to look things up, so it supports queries. Talked a little bit about server-side functions. I can take a function using the grid's APIs and I can deploy it into the grid and use things like, I mentioned event queues, or I could do something that says, every few minutes I want you to count how many objects are in here and give me the result and put it in another part of the grid. Simple example. We saw a little bit about registered interest. This is a specific term that is in Apache Geode, but we talked about how I could have a client and a server, and I could really want to pay attention to a certain object or a certain range of keys that are in my system. And when some of that changes, I want my client to be notified. And we're going to see some cool use cases with that. There's a similar idea that I think we can talk about around continuous queries, where I can write a query to have my client sitting there, and as soon as something changes, I get notified. So let's see that. And event queues. So use cases, really quickly. We'll go through these. Inline caching. Does anyone do inline caching today with any other products? So at a high level, what this is, legacy relational data store. I'm not going to name any, but I'm sure we've all seen them in the wild. They are disk-based, they can be slow, but that's the source of truth. In this case, we can put our in-memory data grid in front of it and provide a lot lower latency data access, reads and writes, into our data grid, or into our IMDGs. So let's just say we have a user comes in, they'll enter some information to a text box, and we want to put that in our database. Our client is going to create an object on that. It's going to be able to put it into our data grid, and then we can say back, yep, we got it. But asynchronously, we can do some write behind into our database. So the data is getting where it needs to go, but from a user perspective, it's getting there much faster. Another pattern that's really common is look-aside caching. This is the case where you have you don't want your client application to necessarily think the data grid is the source of truth. That's the subtle difference. So in this case, same thing happens. I want access to my purple object up there from a user perspective. The client's going to go in. It's going to ask for it. And the first thing it's going to do is it's going to say, yep, I don't have it because it's not cached here. The only place that it resides is in our relational data store. So unfortunately, it's going to have to do the costly thing. It's going to take that much longer period of time that we saw to get that object. But the next time it's requested, it's going to be in memory. And it could even be cached locally in one of our clients. Again, all that expiry stuff would have to happen and make sure that we're actually giving the best source of truth to the entire system. But we're able to provide a much better experience to our users because it's a lot faster. We've also created a pub subsystem out of this architecture. So some object changes within our system. Our magenta object grew, it got some more information. Because of that registered interest function that we talked about, our client is going to just pay attention and says, I really want to know when the magenta object changes. And what we can do is the first thing that will happen is it changes. That change gets brought out to the rest of the grid, and it's also going to get our clients are going to get notified to say, yep, that object changes, hence pub subsystem. Can also do real-time analytics with this type of architecture because you can deploy functions into the grid. So an example, simple count. When a certain there's an abstraction inside of Geode called regions, and that's, think about it, if you're coming from relational world, think about it like a table. So if I go in and my table gets bigger than 1,000 rows, you know, a region has more than 1,000 objects, I want you to kick off a function that I have deployed in here that's going to say to it's going to count everything and it's going to store that result and maybe notify something back. So I can deploy, and these little, I chose a box to represent a function. I don't know if that's the world's best, like a good choice, but it's what Google Slides had. So put up a box, it's running there, and that result is then going to get updated to our client. So we can have this interesting real-time analytics use case, and my clients are being notified at all times. This is probably my favorite use case that I've seen. It's distributed computation. If you go inside of a lot of banks, this is how derivative trading actually does a lot of their work and understands, a bank will understand their position at any given time. So this has been called scatter gather. It looks a lot like MapReduce, but you have inside this cluster, let's just say the price of every stock at any moment in time, and we know it's accurate. We know the position of every single order, every single trade, and it's consistent. So what we can do is we can then spin up a bunch of clients, and each one of those clients is going to take a portion of that data. And then we're going to do maybe some Monte Carlo analysis on each one of those clients. We're going to gather those results back up to say, okay, what's our risk on like this point in time within our system? And we can put that result back into the system. Hence, map and reduce. And because it's all done in memory, this happens really fast. Another thing that a lot of banks do with this type of architecture is they can run a lot of pricing models. So I don't know if anyone works at a bank. I used to be in banking, and a lot of the models are written in C++. So what we can do is we can have clients, they're all C++ clients. They have a really sophisticated derivatives pricing model on each one of the clients. We have real-time, we have updated analytics at any point. We have the source of truth here in our grid, and then we can push these out, and our clients can ask for any updated information on those, and we can do a pricing model on our derivatives at any time. So on a typical trading day, these type of models will get called over 1 billion times. So that's traders saying, okay, what's our position here? I need the price here, I need the price now. And you have to be able to do this in a distributed way and in super low latency using an in-memory data grid. If you want to know more about these types of systems, I can give you this book. It was written by one of my colleagues, Mike Stoltz, and this is, I think, one of the best published pieces on in-memory data grids if you're interested and you want to learn more. So that's all I got. If you want to talk more, I think we have a little bit of time for questions, but I don't have office hours after this, so fire away.
So you mentioned the registered objects. I forget exactly the term. But so does that update communication only happen if you set up some kind of function to actually watch it? Or is there some kind of tracking of if it pulls something into its cache, it just does that automatically?
Both. Yeah, there's both. The API, there's in Apache Geode at least, you can set up a local cache and it will make sure that any updates happen, and there's another way to do it where you, the API is register all keys or register a key, and you can give it a range and say, I really want to pay attention to, for example, anything that's between this date and this date, depending on how you model your data within your grid.
For client caching, do you need to to keep the consistency, do you need to invalidate the cache on every write? So ensuring that acknowledge is received not from the nodes, but also from every single client?
Yeah, so you're exactly right. So if I did some client caching, just to make sure I understand the question, if I did some client caching and a write came in from one of the clients, and you're saying that all the other clients had something locally cached, yeah, we would have to send out a communication to all the other clients to invalidate that, and the system does that. Yeah, because you have to, it's an update to the system, so.